for this afternoon session. So it's my pleasure to introduce Vincent Rivasseau from University Paris-Saclay, and he's going to speak about random tensors, loop vertex representations, and cumulants. Vincent, the floor is yours.
Let me thank the organizer, especially Hammer, who is in both workshops and is an excellent organizer of both. Random tensors, like matrix models, originated in theoretical physics. In the 70s, the first stuff in theoretical physics was to quantize the elementary particles like the gluon and quarks. In this period, matrix model had some success in quantizing the strong interaction. In the 19th, the dominant theory was quantizing gravity was string theory, and random matrix models were seen at this time as a successful theory for quantizing gravity, but only in two dimensions. The inventors of random tensor models, such as Ambion, Gross, Sakura, wanted to replicate the success of matrix models, but in dimension 3 or 4, but they lacked an essential tool, the one-over-n expansion. Let us come to the 2010. The tensor track is an attempt to quantize gravity in dimension greater than 2 by combining random tensor models, discrete geometry, and the renormalization group. I will speak briefly of random tensors. But I think the tensor track is at the crossroad of several closely related approaches on quantizing gravity, most notably causal dynamical triangulation, quantum field theory on non-commutative space, and group field theory. Random tensors share with random matrices the fact that they are an zero-dimension form. And as such, they are background independent. They made no reference whatsoever with any particular space-time. Moreover, random tensor models based on the quantum field theory of Feynman are manageable by renormalization group techniques suitably extended. Simple models even share with non-abelian Gauss theories the property of asymptotic freedom. Je n'en dirai pas plus. Il y a des gens dans la salle qui peuvent répondre plus que moi. Random tensors are expected to play a growing role in many areas of mathematics, physics, and computer science. Communities are using random tensors have grown apart, developing their own tools and results, comme c'est normal. Nowadays, there is an increasing circle of mathematicians and physicists working on random tensors. These people are recently inclined to application linked to the data analysis and artificial intelligence. There is in this room better than me, expert better than me. The line which once separated them from computer scientists becomes a bit blurred. Mais for a long time, I was fascinated by the following question. How to make Feynman graphs more rigorous? I mean, more rigorous from a mathematical perspective. Feynman is a physicist. This is typically a constructive field theory question that was a big question to me by my PhD director, Arthur Breitman. In 2007, I was finally able to say something about this question. I discovered the Loop Vertex expansion, in short, LVI. I asked him to say that the LVI only partially answer this question. For instance, in these initial times, it was limited to the Max-Rich models with chaotic interaction. And what's more, when normalization is absent. Still, I consider it to be a rather new technique of a constructive field theory. For the first time, it applies to Bosoni's field, and a main feature of the LVR is that it is LVE is that it is written in terms of trees which are exponentially bounded. It means that the outcome of the LVE is convergent when, whereas the usual perturbative field theory, that of Feynman, diverges. In Razvan Guru, you for those of you that has been to the talk of Rashvan Guru on series, it's obvious. The LVE does indeed converge. The next question is which sum? To which sum? Answer, it converges to Borel sum. The essential ingredient of LVE are the intermediate field. In physical parlance, the Rivasseau field. And the BKAR formula, developed by David Bridges, Tom Kennedy, and perfected by Malek Abdesalam, me, and Zichuo Wang, who is in this room. In 2014, Thomas Krajewski and Rajan Go solved that an LVE method, the main constructive problem of the cumulants their paper I think the main constructive field theory of cumulant, but for an interaction limited to 4. In 2016, I discovered the refinement of LVI, which are named LVR. The added ingredient of the LVR are essentially combinatorial, based on selective Gaussian integration and the generative function of Fuss-Catalan numbers. I think that the LVR has more power than the LVE, since the LVR can treat more models with higher polynomial interaction. It converges to the Borel-Leroy sum. Leroy was a PhD student of Borel. It has been developed and perfected from approximately 6 years by Thomas Krajewski, Vasily Sazonov, and me. Thomas has added the holomorphic matrix calculus of Cauchy and Vasily has recently and beautifully applied selective Gaussian interaction in the quantum field theory formulation of the Jacobian conjecture. LVR has an additional parameter pi, the degree of the polynomial interaction. Hence, the partition function for Wishart complex matrix ensemble is Z to the D of lambda and n. equals integral with respect to the dm of exponential minus trace of mm dagger plus trace of the interaction. In this formula, you can discover the parameter p. E equal 2 is equivalent to the quartic interaction. But in this case, LVE is sufficient, and LVR is really necessary from P equals 3 to infinity. In this the case P equals 3 and 4, the LVR is somewhat simplified. The Fuss-Catalan equations for the generated function is Z T3 of Z minus T3 of Z plus 1 equals 0, which is soluble by radicals. It's not soluble by radicals from P equals 5 at infinity. Let the partition function be the P of lambda and J. The Cumulants are K, P of lambda and P and G. Left me fix Kmax. Mijn main result extend to higher interactions P equals to from 3 to infinity. The results of Rivasseau and Gouraud in 2014. Let K less than K max, the expansion 1 is absolutely convergent in the cardioid domain C. The expansion is analytic for lambda belong to C and is Borel-Leroy summable. The proof holds uniformly in the external variable. Details are available in the corresponding paper by me in May. Here is a picture of a cardioid domain in the case P equal to 3, and remark that the value 1/4 is exact. The crux of the LVR lies in the matrix valued function A, and the functional change of our variables from M to X, such that A of lambda and X is equal to X times T P of minus lambda X to the T minus 1, so that equation 1 can now be written as X equals A plus lambda A to the E. We define d mu, sigma, S, and kgn by the following formulas, so that the formula for the moments of the partition function is sigma. You can read the formula. Our goal is now to deduce the formulas for the cumulants K, which are the connected moments. And we want to factorize I will sketch the proof of our main result. In the first step, we defined W equals W1 plus W2. And we expand to infinity the exponential of the interaction, provided Wi equals W. The second step is to introduce replicas and to subtly replace the integral of the single n times n complex matrix M by an integral over n tuple of such matrices Mi. In the first step, we shall perform the BKAR expansion. After the BKAR expansion, we perform the Cauchy holomorphic matrix calculus introduced by Thomas Krajewski, and the partition function with sources f of k is, I let you the time to read the formula because it's quite complicated. Remark that this formula does not require the intermediate field because it is defined as a Gaussian integral over Ix I equal 1 over n mi dagger. Si vous avez des questions, je vais les prendre. Et log Johan plus et voyez cette vraisemblance. Hein. That's not require the intermediate field. No question?
Will you later tell us about Kmax?
Oui, oui. Kmax j'ai besoin de Kmax parce que je dis que Kmax pour la partie uniforme, j'ai besoin.
You need it.
Oui.
Yeah, so for the non-French-speaking people, he said he needs this Kmax cutoff to ensure uniformity in the probably external variable and
Oui.
capital N,
Oui.
so size of the matrix.
Oui. Dans mon bac-pied, je définis G cumulant et topological cumulants, mais je n'ai pas fait la distinction entre topological cumulant et G cumulant.
Okay, further details in the paper.
Now, our results can be summarized as a convergent expansion of K as a sum of LVR trees with K cilia of formalism incidentally affect the formula of affiliated trees to Leonard Ferdinand, who is just the speaker after me. Since the field, the measure, and the integrand are now factorized over the connected component of F, its logarithm is computed as exactly the same sum, but restricted to the spanning trees. Cette formula simply replace F by T. After some combinatorial tricks counting the cilia, the trees, this concludes the proof. Leonard that is an expert on this counting cilia and trees. Now, please, we will pass to the work of Wassily Sazonov on the Jacobian conjecture. The Jacobian conjecture can be formulated as follows. Let F be a polynomial map written as F equals F1, etc., Fd, when X1, etc., Xd are coordinates and the functions Fi are polynomials. Hereafter, we shall write just X for X1, etc., Xn. Suppose that the Jacobian determinant Gf is identically a non-zero constant. Without loss of generality, it can be fixed to the value Gf equals 1. So then that the F is globally invertible in the sense of composition, and its inverse G equals F to the -1 is also a polynomial map. It can be formulated around the time of Jacobi, but it is formulated in a little known paper just about the Second World War. The AR model is defined by the action equal to the power series of the first cumulant of the model G or K, and of Y equals 1 over Z equal integral over d psi divides phi k exponents of minus k. And and is a convergent form small y's. See the work of Salam in 2002. This reduces the proof of the Jacobian conjecture to prove the vanishing of all the coefficients after a certain order of the perturbative series. Now I pass to the specific work of Sazonov. It has been perfected by Sazonov for about 6 months. It's the work is entirely combinatorial. It makes no reference to fancy theorems such as the Bauer theorem. Tout l'arsenal de la combinatoire et de l'algèbre. It's entirely combinatorial. Here is an example of a tree with D equals 3 and V equals 3. You can see the vertex, free vertex, and ternary trees, directed trees. And it's the vertices initially contain the trees. Là, 7 leaves and different colors from D equals D colors. Is it possible that color trees can contain some change of vertices of the length greater than n? Here is an example of a tree of a not specified order. You can see the line. The line in 20 dashed. Can the change circled by a blue line and orange line, blue line and orange line, be longer than n? This question is equivalent to the question about the maximal possible depth of the tree and is directly related to the proof of the Jacobian conjecture. Reste à savoir la signification de not specified.
But that remains to define what it means by not specified order. Are you going to explain?
Well, non. Non. Vassili Sazonov est dans la salle. Il expliquera toutes vos questions mieux que moi.
So you got that. If you have questions about this part of the talk, you ask Vassili,
Oui.
who's here.
If this conjecture is false, is the Jacobian conjecture false?
No.
So explain directly related. What is the direction of implication?
Ah oui. If the statement is correct, the Jacobian conjecture is correct, but not the converse.
Thank you.
Termination of the series. For trees with a maximal depth n equals to 1, in -1, the maximal number of leaves is d to the n-1. In parts in
1982.
82, Bass and O'Connell and Wright all reduced the Jacobian conjecture to the case D equals 3 for any n. I think the argument of Vasily Sazonos and is correct and optimal in the sense that it works for any homogeneous polynomial and make no use of the reduction of Bass and O'Connell and Grad. I could be wrong, but I think that the Jacobian conjecture has now become the Jacobian theorem.